Okay, finding equilibrium concentrations. We talked about how to calculate K, the equilibrium constant, and we learned that you could do that from the equilibrium concentrations or from the initial concentrations and one equilibrium concentration. That was the ICE table we learned about last week. Now we're going to talk about kind of the opposite, where we know the equilibrium constant. How do we find out what the concentrations at equilibrium are? So there are two categories of problems here. In the first one, we know what the equilibrium constant is, and we know all but one of the equilibrium concentrations. So this one is pretty straightforward. We write the expression for K, and then we plug in the numbers and we solve for the unknown. The other situation is more common, and that's where we know the equilibrium constant and we know the initial concentrations. This is much easier to know. Measuring equilibrium concentrations at best is a pain and is tedious and time-consuming. We can set up the initial concentrations to be whatever we want. We can know what those are. We can look up the equilibrium constant for a given reaction at a given temperature. So if we have that situation, then we need to use an ICE table. Okay, so let's look at the first example, first type of problem first. We'll do the first thing first, right? So here we've got the equilibrium constant and all but one equilibrium concentration are known. So here we have diatomic iodine decomposing to form iodine atoms according to this reaction. In an equilibrium mixture, the concentration of I2 is 0.10 molar. What's the equilibrium concentration of I? So we are going to write the equilibrium expression using the other pen. So we've got concentrations here. So this is Kc. And that's going to be the concentration of the products divided by the concentration of the reactants. Right? So what we have here, I'm just going to rewrite this expression, putting in the numbers that we know. So we know that Kc is 0.011, because they told us that right up here. And that's equal to the iodine atom concentration squared divided by the I2 concentration, which is 0.10. So here I plug the numbers in, and then we're going to solve. You could also rearrange this, solve for I, and then plug the numbers in. So you can use your solver to do this, or we can multiply both sides by 0.10, which gives us I squared. And then we'll have to take the square root of that. This is going to be the square root of 0.011 times 0.10. Looks like we've got two seg figs, so I'm going to write down. You got something else? Okay. Oh, okay. I think my calculator is just set for scientific notation because it was. So that's the same as 0.033. Any questions? It should be fairly straightforward. Doesn't mean it is on a Monday morning, but it should be. Yay, we got it correct. So there's a unit here, right? This is unitless, right? How do we know what unit to put on this concentration? What does it have to be? Has to be molarity, right? Because it's all set up that way. The reason there isn't a unit there is that technically what we've got is we've got the concentration of I over 1 molar. They are all ratios, and that's why the units go away. It's one of those little trivial points. Okay, before the reaction A goes to 2B, Kc is 4. The reaction mixture at equilibrium contains 1 molar A. What's the concentration of B? So this is a conceptual question, so in theory we shouldn't need a calculator. It doesn't mean we won't need to think about numbers, though. I like the number part, and so I like to, write some stuff down here, right? So the equilibrium constant is equal to the concentration of the product squared over the concentration of the reactant. And so they're telling me that the equilibrium constant is 4, and that A is 1 molar at equilibrium. And then they're asking me what's B. B is C, yeah. It's going to be 2. If the concentration of B is 2, 2 squared is 4, divided by 1 is equal to 4. Does that make sense? Any questions about that one? Okay, the more common type of calculation, which involves a little bit more work. So here we need to follow a specific procedure. So we're going to set up an ice table with the initial concentrations. Those will be given. We're going to represent changes in concentration in terms of X, and that's going to be done considering the stoichiometry of the reaction. We're going to add the initial and change rows so that we can find the equilibrium concentrations in terms of X. And then we'll plug those into the equilibrium expression and solve for X. And this technique is going to be used in this chapter and in other chapters. So it's important to learn how to do this. It's not going to go away in this class. So we'll start with a simple example here. A going to 2B, equilibrium constant's 0.33, and the concentration of A is 1. So we have our initial change equilibrium, that's our ice, and the initial concentration of A is 1. They don't say anything about the concentration of the product. We can assume that that is 0. Then we're going to look at the stoichiometry here and see, well, what's going to happen, and we're just going to call the change X. So A is going to decrease by X amount. We don't know what that is. And B is going to increase by 2X. Right? Because for every one of these that you break down, you form 2 of those, right? So that's why we have a 2 here. Everybody with me? So then we're going to take the initial plus the change, and we're going to get the equilibrium concentration, except it's not a concentration, it's just a thing in terms of x. All right? So then we need the equilibrium constant expression. So K is equal to B squared over A. We know what K is, and we know what these equilibrium concentrations are in terms of X. We're just going to plug everything into this. We're going to get 0.33 is equal to B, which is 2x squared, divided by A, which is 1 minus x. Solve for x. Well, this is going to be a quadratic equation, right? Remember the quadratic formula? Yeah. I remember there is a quadratic formula. I could look it up and use it, but why? I have a TI-36X Pro. So other calculators like the TI-84, etc., can solve these as well, but it's not as intuitive. So on the TI-36X Pro, what we're going to do is we're going to go to the number solver, and if we've used it before, it's got whatever we did last in there. We're going to clear that out. I'm going to put this in exactly as I've written it. I don't need to rearrange anything. It's beautiful. So on the left side, I'm going to type in 0.33. I'm going to move the cursor over to the right side, and I'm going to use that nice fraction button. I didn't mean to do that. Fraction button, and I'm put it in parentheses 2 in the variable x, and I'm going to close the parentheses, and I'm going to hit the x squared button. So it looks just like this. And then in the denominator, I've got 1 minus x. I press equals. It's got x equals the last thing I did. I'm just going to start out at 0, because that's usually a good place to start. And I'm going to solve. So my solver is showing me that x is equal to 0.2489. I'm looking here, we're probably doing 2 sig figs here. So that's x. Anybody need help getting their calculator to show them that? I'm going to go back and start with a different x. I'm going to start with minus 1 and see what I get. If I start with minus 1, I get x is equal to negative 0.3314. Quadratic equations often have 2 roots, right? One is positive and one is negative. This calculator will solve for the first one it comes to. And this is where the number you started out on can affect the answer you get. But only because there's actually 2 answers, right? So this one, I did it with the solver, and I started on x equals 0, and I got a positive number. If I wasn't trying to make a point, I would just say yay and go on. But just, to show you what can happen, I started with x is equal to negative 1, and it found the negative root for me. In these tables, we need to have positive concentrations, right? So here at equilibrium, the concentration of B is 2 times x. can this negative x possibly be correct? No, because that would give us a negative concentration, which is just physically impossible. So that's not the one we want, okay? What happens if you start with 0 and you get a negative answer? Try it again. Don't start at 0 this time. Try 1 or -1. Usually that'll take care of it. Sometimes you have to do a little more. Okay, is this the answer to our problem? What are the equilibrium concentrations? No, we just found out what x is. Now that we know what x is, we know that the equilibrium concentration of A is the initial concentration minus x. You can get your calculator to show you the value that you just calculated by pressing that variable button. Here we just use x and press equals, and it'll show you that number that you just calculated. Took me a while to figure that one out. So 1 minus 0.2489, 0.7511. Wait a minute. Here, subtracting, this is to the nearest ones place, and so if we're going to be picky, we're going to call this 0.8 molar. I don't think saying 0.75 molar is a horrendous thing. It's ballpark. And then what is B? Well, B is equal to 2 times x. So 2 times 0.2489. And that is 0.4978. Which would be 0.50 molar. And here you could argue that that should only have 1 decimal place as well. And this is where, we just don't take sig figs too seriously. We use them as a guideline, right? We don't want to say that the concentration is 0.4978. That is misleading the reader, suggesting that we know it to 4 decimal places when we definitely do not. Any questions? You see the process there? We're going to do this process again and again and again. So you might want to make a little flashcard for yourself or a note on your phone with these steps. And a good way to learn the steps is to try to remember what to do and then look at the list. Don't just always go and look at the list. Try to remember it first and then check the list. Okay, consider this reaction. N2 plus O2 goes to 2. No! The reaction starts with only the product and no reactants. Here they're nice and specific. Find the equilibrium concentrations of N2, O2, and no. We need an ice table. I like to use the chemical equation as the header for the ice table. So here it's up where I can't just draw over it, so I'll have to write it down here. N2 gas plus O2 gas in equilibrium with 2 NO. So that's my header row. And then I'm going to have I and C and E, ice. And I'm going to draw lines here. I'll put a double line there. I don't think I've ever done that in lecture before. It just occurred to me this semester that might be a helpful thing. So we're given initial concentrations. Let's write those in. So the concentration of no is 0.0100. All the concentrations are going to be in molarity. So if you want to leave that off, that's okay. What were the concentrations of N2 and O2? 0. It said there was none. So 0. So now I'm going to identify how these concentrations are going to change in terms of X. The N2 concentration is at 0. It cannot get any lower, right? It can't go down. It has to go up. And the coefficient here is 1. So this is going to increase by X. And the other reactant is also going to increase by X. We don't know what the change is. There's a 1 here, so this is 1x as opposed to 2x or 3x or something. Over here, we're starting with this, and this concentration is going to go down, so this is going to change by subtracting. And there's 2 of these. So this is going to be minus 2x. Okay? Everybody okay with that? So now we're going to add I and C to get E. So this ends up being X, and this is X, and this is 0.0100 minus 2x. Do not try to do the ice table in your head. Just don't. For the real simple ones, you can do it. But we need to learn how to do the ice table, because I guarantee you I'm going to give you questions on the exam where I can't do it in my head, right? You have to write it down. So now's the time to practice writing it down. Okay, so now we've got our equilibrium concentration in terms of X. We're going to write the equilibrium constant expression. Kc is equal to no squared divided by N2 times O2. That's what we learned at the beginning of the chapter. We're going to take these equilibrium expressions, the values here, and Kc, and we're going to put them together. So Kc is 0.055, and that is equal to NO squared. So NO is 0.0100 minus 2x, and that's going to be squared. And this is divided by x times x. You see what I did there? Each of the little steps is not bad at all, but we have to remember what the order is, right? And be careful. So now we're going to solve this for x. So you could do algebra there and solve it for x. But I like algebra, and I don't want to do that. I'm going to use my solver, right? Why not? So I'm going to go to my number solver and clear out that last thing that I did. On the left, I have 0.055. On the right, I have a fraction, so I'm going to use my fraction button. Now, you do have to type it in correctly, right? So I have parentheses around this expression, so I'm going to use the parentheses when I type it in here. I've got 0.01 minus 2x. I'm going to close the parentheses and square that guy. And then down in the bottom, I can do x times x, or I could call that x squared. I'm going to call it x squared, and then I'm going to press equals, and I'm going to start this guy at 0 because that usually works the best, and I'll wait a few seconds to see what it says. It tells me that x is equal to 0.0044752. This guy has 3 sig figs, that guy has 2. Were you able to get that number? Takes a lot longer if you use the quadratic equation. And then we have to remind ourselves that even though we solved for x and we feel really great about that, that's not the answer, right? So we want the equilibrium concentrations. Well, the equilibrium concentration of N2 is equal to x, right? So that is equal to 0.004, and I'm thinking 4.5 is probably generous number of sig figs there. And for the O2, that one's also equal to x. But our product here is going to be 0.0100 minus 2 times 0.004475. I'm including a couple extra digits here to avoid possible rounding errors. 0.01 minus 2 times 0.004475. 0.00105. So, just thinking about significant figures, this concentration was originally known to the 4th decimal place. We're subtracting something from it, but the 4th decimal place was uncertain. So in our answer, the 4th decimal place is technically uncertain as well. This is a fine answer, in my opinion. If we want to be strict with our sig figs, it should be 0, 1, 1. 4 decimal places. And you could definitely argue that these should be 0.005. Let's see what the book says. Oh, okay, cool. Any questions? I guess I should box these guys too. So there's 3 answers. Any questions? Okay, consider this reaction. N2O4 goes to 2NO2. Equilibrium constant is 0.36. Reaction mixture contains only the reactant and no product. Find the equilibrium concentrations. So, same process. Make an ice table. Put in the initial concentrations. Find the change. Add the initial and change to get the equilibrium concentrations. Plug that and K into the expression solve for X. So I've got N2O4 is in equilibrium with 2 NO2. Ice. Initial concentration, N2O4, 0.0250, and it says we only have the reactant. That means the product is 0. How does the concentration of this reactant change? Does it go up or down? Down. How much? X. We don't know exactly how much, so we're going to call it X. If this goes down by X, what happens to this one? It goes up by 2X. Aren't those coefficients nice? They just tell us exactly what to do here. Okay, and then we're going to add those top two rows together. So this is 0.0250 minus X, and this is 2X. I'm going to write the equilibrium constant expression. I think this is worth your time, just to make sure that you're not forgetting something when you're doing it in your head. So product is on top, coefficient is 2, the concentration is squared. Reactant is on the bottom, coefficient is 1, and so it's just 1. And now I plug in the Kc is 0.36. NO2 is 2x, so that has to be squared. And that is divided by 0.0250 minus x. And again, I think it's just easiest to go to the solver. 0.36 on the left, fraction on the right, in parentheses, 2x squared. You need to put those parentheses in there because the 2 gets squared as well as the x. And then in the denominator, I've got 0.025 minus x equals, let's start with 0 again. X equals 0.02038. Any questions on how we got X? Is your calculator giving you the same answer? Because sometimes I do it wrong. So now that we have X, we can figure out what the equilibrium concentrations are. So for the N2O4, that was 0.0250 minus X. So that's 0.0250 minus 0.02038. Zero 0.00462. And where should we probably round that number? Remember, rules for subtracting, whichever has the fewest decimal places, that's how many decimal places the answer has. So the answer should have 4 decimal places, 0.0046 molar. I will not try to trick you with sig figs. But if you have a multiple choice question and one of the answers is 0.0046 and you're coming up with more digits, then you need to recognize, oh, well, that's just rounded, it's the same. Don't think, oh, it's none of the above, or Mrs. K made another mistake on the exam where there wasn't a correct answer for the question. Sorry about that. Okay, so there's the one, and here's the other one. 2 times x. So 2 times 0.02038. So this is 0.04076. And then I was like, well, what do we do with the sig figs here? I mean, you could look at this and say, well, 3 sig figs. I could round this to 3 sig figs. Or you could say, well, this one is known to the 4th decimal place. I'll round this one to the 4th decimal place. Both of those, in this case, are going to give us the same answer. So I'm going to go with that, 0.0408. I don't remember what the book says, but that's what I'm going with. Something to remember is that in these types of reactions, these concentrations are very rarely known precisely. So 2 sig figs is kind of normal. Okay, so they rounded a little bit more. 0.005 and 0.041. Okay. Am I wrong? No. Is the book wrong? No, we can both be right. Any questions? Okay, so here we have partial pressures instead of concentrations, instead of molarities. It works the same way. When we're dealing with partial pressures, the partial pressures always have to be in atmospheres. So we've got a reaction, we've got a KP. The reaction mixture contains both reactants, each with a partial pressure of 0.150 atmospheres, and no product. Find the equilibrium pressures of all 3. So we're going to make an ice table. Yep, we're going to make an ice table. I2 plus Cl2 in equilibrium with 2ICl. Ice. I made my ice table. Now I'm going to put in my initial pressures. So the partial pressure of each reactant is 0.15 atmospheres. And there was no product. How do these reactants change? Minus X. Right? They're going to go down. We don't know how much. We're calling it X. How does the product change? It goes up 2X. And this 2 is because of the coefficient 2. Then we're going to add these together. 0.150 minus X, 0.150 minus X, 2X. KP is equal to the partial pressure of ICL squared divided by the partial pressure of I2 times the partial pressure of Cl2. Same format, just partial pressures instead of molarities. 81.9 is equal to 2x squared divided by, now I can simplify this a little bit. Each of these is equal to 0.15 minus x. So instead of writing all of that out twice, I'm just going to say 0.150 minus x, the quantity squared. And again, I'm going to use my solver. So I've got 81.9 on the left. I've got the quantity 2x squared. I forgot to push the button. Oh, that's cool. I pushed it and now it made a fraction. And then on the bottom, I've got in parentheses 0.150 minus x, close the parentheses, squared. Start with x equals 0. Zero 0.12285, blah, blah, blah. If we get a negative number, then we have a problem. Yeah.
What if we get two positive numbers?
Pardon me?
What if we get two positive numbers?
That's a good question. What if we get two positive numbers? Only one of them is going to work. Only one of them is going to work. So, what's the other one that you got?
0.192.
0.192. Okay, so there are two roots. If we come up with this one, and we go to calculate this pressure, and we have 0.15 minus 0.192, we get a negative pressure. Is that possible? No, it's not. And so that's how we can tell that that one doesn't work. Only one of them will work. Sometimes it comes out negative and you're like, oh, that's obviously not good. Other times it comes out positive, you're like, great, and you go calculate your concentrations or your pressures, and you end up with negative ones, and you're like, what did I do wrong? We didn't do anything wrong, you just need to find the other root. It doesn't happen too often, but it does happen sometimes. So, oh, not concentration. So the partial pressure of I2 is equal to the partial pressure of Cl2, and is 0.150 minus x. 0.150 minus 0.12285. And that was a great question, and thank you for asking. 0.150 minus 0.12285. 0.02715. I'm probably going to call that 0.027 atmospheres. And then the partial pressure of our product is 2 times x. .2457, and probably call that 0.25 atmospheres. Well, actually, these guys were 3. I'm going to go with 3, 4, 6 atmospheres. And let's see if we agree with the book. So, questions? when you're doing this intermediate stuff, always write down a couple more digits than you think you're gonna need. 'Cause then you come to the end, and maybe I rounded that to 0.03, and then I type it into the computer and it says, it wants more sig figs. Well, no problem. I can go back and look at my unrounded value and give it more sig figs. Not a big deal. If I round off as I'm going along, I've lost that information. If I need it back later, I have to do the whole stupid problem again. And I might end up with rounding errors. You know, if we get this and we round it to 0.1, that's not cool. It's throwing away information. Any questions?